Then today, let's discuss mainly about singular value decomposition, and also moving to the lecture 4, which is about the projection. Yeah, so yeah, we will maybe move back and forth between, discussing between this projection stuff and also QR decomposition and SVD from the perspective of a singular value decomposition, the projection. Okay. So we had some other lecture material about singular value decomposition, right? And then we discussed about this change of a basis, right? So yeah, when multiplying the matrix A, and then we decompose it into 3 parts as a result of a eigen decomposition or singular value decomposition, and then if we consider this eigen decomposition, and then those 2 matrices should have the inverse relationship, and then the first one is changing the basis of a given vector with respect to the eigen basis, right? And then we extract out the coefficient, right? And then if we have this x vector, and then we are given these 2 eigen vectors, and then we first represent it as a linear combination of these 2 eigenvectors, okay? And then those linear combination coefficient is called the new coordinate with respect to the basis of this eigenvectors, or it is also called the eigen basis, okay? Because we are defining newly, we are newly defining the basis of a same space by using eigenvectors, okay? And then once we obtained or computed this coefficient with respect to this eigen basis, and then the next next step will be multiplying this matrix D, which is our diagonal matrix, right? So multiplying the diagonal matrix with the given vector is just a scaling, independently. I mean, the scaling each coordinates independently or separately, right? So they do not combine. They do not combine the values or the elements across different dimensions, right? So that is the main point, right? And then once we do the diagonal scaling, and then we go back, we come back to the original coordinate space by just multiplying or linearly combining the eigenbasis that we used in order to get back to the original coordinate value with respect to our standard basis of 1, 0 and 0, 1. Okay. So that was the main idea when multiplying the matrix A by representing it as a eigen decomposition. And also the singular value decomposition follows almost the same scenarios. Okay. In the case of a singular value decomposition, now we do not have a restriction that the matrix should be square. So our matrix can be any rectangular matrix, right? And then now also, comparing between eigen decomposition and the singular value decomposition, this matrix in the middle is still diagonal matrix, right? And then in the case of an eigen decomposition, those 2 matrices should have the inverse relationship, and eigen decomposition only is defined only for the square matrix. So all the 3 matrices should be square matrix. But in the case of singular value decomposition, if we have maybe 5 by 3 matrix, and then U is defined as 5 by 5, and this sigma is defined as 5 by 3, and it is 3 by 3, right? And so now the matrix can be rectangular, especially in the case of this middle matrix. And also these two matrices on the left and the right, they can now be a different matrix, right? So now we have a additional freedom to represent this matrix A as a product of these three pieces. But now the first and the third pieces can be just a different or separate matrices. So we now have a freedom, more freedom compared to the eigendecomposition. So in that sense, eigendecomposition is not always defined for a given given square matrix, right? But in the case of singularity decomposition, because we have more freedom, and so it is always defined for any given rectangular matrix, right? So that is another kind of intuition that we can maintain. And also, giving those two separate matrices on the left and right, you can think of it as a kind of having too much of a freedom, and so we impose some restrictions so that U and V are orthogonal matrix, which means that those vectors are not only linearly independent, but also they are just orthogonal to each other, right? So also intuitively, this orthogonality is a kind of much more strict condition than linear independence. So you can kind of intuitively think of this orthogonality as like a maximally kind of linearly independent. So for example, if we consider the angle between these two, and then if the two vectors have the same angle, and then they are linearly dependent case. But if they have some angles, and then if that angle is maybe 0.001, and then just because they have a different angles, so they are linearly independent. But as I mentioned maybe a month ago or so, if the two vectors have almost zero angles, and then they can cause some instability. They make our computations unstable, right? So so just to remind you guys, so suppose we want to solve this standard linear system of an AX equals B, and then A is, you guys know that so we have a B over here, and then suppose the A has a two columns, and then the first column and the second column is like this, and then solving this X is the same as solving or computing the corresponding vector lengths or the scalar multiple of these given basis vectors, right? But let's think of these two vectors are really pointing to the same direction, and then suppose we have some point over here as our B, and then it is a little bit difficult to draw, but how can we make that point? Maybe we can strengthen this a lot, and then maybe the first one can be like this one. Okay, although the shape is really ugly, but you get the idea, right? So if their angle is so our computation was a little bit approximate, which actually happens in our computers, right, using a finite precision, right? And then suppose our angle should have been like 0.001, but our computer happened to compute that angle as 0.002, for example. And then their coefficient can be really resulting in a completely different solution, right? So that creates, that is the main cause of bringing some instability of our solution, right? So from this approximate kind of computational environment, which actually correspond to our computer case, and then it is generally good to have the basis vectors having like as large angle as possible. Okay, which means it would be great if they can have a maximum angle of 90 degrees. I mean, if the angle is greater than 90 degrees, and then we can think of the other side of an angle which is still less than 90 degrees. So the maximal angle that we can achieve is 90 degrees. And so this kind of close to linearly being linearly dependent. I mean, that causes a lot of problem. So in general, it would be great if we have a maximum angle linear independence among our basis vectors. Okay, so in this case, how can we improve this situation? I mean, suppose we are given these really close basis vectors in terms of their direction or angles. Then we can first pre-process this matrix A by applying or computing the QR decomposition, right? So in the case of QR decomposition, instead of just directly solving for the coefficient of a given vector B with respect to our basis, we can first orthogonalize these given basis vectors so that we can convert or change them into maximally linearly independent vectors. Okay? So that is a kind of one idea, or the practical needs or the practical use of applying the QR decomposition in advance. I mean, before solving this actual linear system that we need. Okay, so back to this SVD form. U and V will give us the maximally or linearly independent kind of vector set. Okay, and also you guys know that like the column space of an A. I mean, we have to discuss about this reduced SVD form. I mean, you reduce the form of an SVD. So if I use the full SVD, and then if our matrix is 5 by 3, then as I mentioned, this U is a 5 by 5, which is a square matrix, and then 5 by 3 and then 3 by 3, right? And then you guys know that, if we ignore this matrix in the middle, then multiplying this left and the right matrix can be viewed as the sum of rank 1 outer product of like matching the first column and the first row, and then form the really large matrix which still has a rank 1, and then the second column and the second row, and then create another matrix and then add them together, right? And then what if we have, we have a diagonal matrix in the middle, right? And then those diagonal elements will work as like a scaling factor corresponding to the first outer product and the second outer product and so on, right? So that is the intuitive role of this diagonal matrix. Okay, and then so we have a 5 by 3 matrix as a kind of I'm not even sure if we can call it as a diagonal matrix, because diagonal matrix is only defined for the square matrix, but it's a rectangular matrix that has the same size as the input matrix. But here, inevitably, we will have a diagonal elements along this shorter kind of axis, right? So in the case of 5 by 3, then we will only have like 3 non-zero diagonal elements, right? Because it will end here, right? So from the perspective of a scaling factor of each rank 1 component, okay, and then we only have a maximally 3 non-zero scaling factor, right? So given 5 by 5 and 3 by 3, then like this scaling factor, non-zero scaling factor will only have a 3 numbers, 3 values. And so we can safely remove these redundant or like additional parts, and then also this additional parts. So that is the main idea of this reduced SVD. Okay, so this is a smaller version that we just saw in the previous slide. And then once we decompose it into a scalar multiple of this rank 1 outer product and their sum, okay, then we will only have a 3 non-zero elements. And then if we just rearrange them as a matrix product form, then now our matrix over here on the left will have 5 by 3 and 3 by 3 and 3 by 3. Okay. Okay, and then now in this case, this part is no longer be a square matrix. It's a rectangular matrix. And then this rectangular matrix, I mean, we're talking about the orthogonal matrix. Orthogonal matrix is the notion for the matrix defined only for the square matrix, right? But now it's a rectangular matrix, but still it will have orthonormal columns between each other, right? Okay. Okay, then let's see. Yeah, from the perspective of this reduced SVD form, there are some interesting characteristics that we have to have in mind. So, for example, given this we still use this running example of a 5 by 3 matrix. Okay, then let's see the column space of an A, right? So, what is an A? A is a 5 by 3 matrix, right? Okay, so we have 3 columns, right? And first of all, what is the rank of the column space of an A? We have 3 columns, and their span, I mean the definition of the column space of a matrix is the span of all the given columns, right, existing in our matrix A. So maximally, it will have the rank of a 3, or the dimension of this subspace will be 3 or less, right? And then here in this case, okay, so this guy is the same as the column space of U in the case of this reduced SVD form. So this is U and sigma and V. Okay, so intuitively, what this tells us is the given the same column space of an A is the same as the column space of U, which means that U provides the orthonormal columns, right? So the columns of U is actually, I mean, that works as the really clean or like orthonormal basis for our column space of a input matrix. Okay, so again, it's like it can be viewed as kind of QR decomposition, because I mean the column space of an A, we now obtained the orthonormal basis. I mean version of a really nice basis, which is an orthonormal basis for the same column space. Okay, and also similarly, column space of an A transpose. Okay, A transpose is column space of V. Okay, so this is V transpose, right? And then there are some other additional relationships. What about the null space of an A? So the null space of an A. Okay, so let's first think of the dimension of this space. I mean, the entire space that contains this column space of U is 5-dimensional space, right? And then A transpose is 3 by 5, right? 3 by 5. And so this guy is 3-dimensional space. And then now let's consider the null space, right? The null space is what? All the set of the solution of this AX equals 0, and then this this X is a 3-dimensional space, right? 3-dimensional space. You know that, right? 이건 알죠? 그 null 스페이스가 3차원인 건 알죠? Yeah, sure.
What will the dimension be?
Oh yeah, we are still using a 5 by 3 as our matrix size. So in this case, the column space is basically the column, the span of these columns, which are still 5-dimensional. So the column space is in the 5-dimensional space. But what about the null space in this case? So the null space is like A times X should be equal to 0, right? So 0 vector is 5-dimensional space, but X, the vector X that is multiplied on the right side of this matrix A should be 3-dimensional space.
Not 2-dimensional.
Huh?
It's not 2-dimensional.
Oh, should it be 2-dimensional? Okay, so 4, 2. Okay, so it is an example of 5 by 3, and then the X vector should be 3-dimensional space. Okay, so we know that these three values work as a linear combination coefficient of these 3 columns, right? Okay, and then if we set this B part as all zeros, and then collecting all the possible solutions, okay, that satisfies this equation. So that set of the vectors, is called the null space. So that is the main or basic definition of the null space. And then I mean, if you want to review or remind yourself of how to compute this null space, and then you can maybe go back to some of the undergrad level linear algebra book, and then it should give you how to solve or how to compute this basis of this null space, which is just a byproduct, or which just naturally comes out of just a Gaussian elimination. Okay? So once you solve this Gaussian elimination, and then you can just obtain the basis of this null space. Okay, so due to the time limit, I'm gonna skip that part, although I'd like to, but so you can just go back to those undergrad book, and then you should be able to find it easily. Okay, and then this null space of an A will have some set of bases, but we know that there are many different versions of a basis given the same subspace, right? So just like this, column space of an A can be spanned by the original 3 columns, which are not necessarily linearly independent, but we now have this columns much nicer set of bases which are orthonormal that spans out the same subspace, right? Similarly, this null space, when just applying or when computing Gaussian elimination and then obtaining the basis for this null space, okay, in that case they are not necessarily orthonormal basis, right? But if you want to obtain orthonormal basis, and then you have to do additionally like this QR decomposition given this basis vectors that we obtained from Gaussian elimination, right? But once you obtain the SVD, okay, SVD, and then you can just automatically or naturally obtain the clean basis vector, orthonormal basis vector for this null space as well, which is okay. So it is a 3-dimensional space, right? So the basis intuitively the basis comes out of this part, V part, right? V part, right? Because we are at least we are dealing with a 3-dimensional space, right? But here, in this case, if our sigma or this singular value is, singular values are all non-zeros. For example, suppose we obtain the singular value as maybe 8 and 5 and 2. Okay, so in this case, we have no null space. So in this case, this guy is just, this guy is just containing 0. Okay, but suppose we have suppose we have the number of non-zero singular values strictly less than or strictly smaller than the minimum of a m and n. So m is 5 and n is 3. Okay, and then the minimum between these two numbers is 3, right? But if we have strictly smaller, smaller singular value, then it's 3. For example, in this case, 8, 5, and maybe 0. Okay, so in this case, this null space of an A, null space of an A is, the basis, orthonormal basis is this vector, the last one, corresponding to this guy. Okay, so I'm not giving you the proof, rigorous proof, but it's kind of easy to kind of memorize or understand, I believe, right? So I'm just giving you some kind of intuitive meaning. Okay. Okay, so here the main point again is, let me rephrase it. So given these reduced form, and then suppose our matrix is maybe 100 by maybe 50, 100 by 50, and then in terms of this reduced form, then we will have 50 by 50 diagonal matrix in the middle, right? And then suppose we have only 30 non-zero singular value, and 20 of them will be 0. Okay, let's assume that. Okay, and then this one will be 50 by 50, 50 by 50, but corresponding to these 20 non-zero ones. And then we will have these corresponding 20 orthonormal vectors, right? And then that will be the orthonormal basis of your null space of an A. Okay.
스페이스는 콜럼 스페이스가 좀 세시니까 원소 기호가 아니라 공집합 기호.
네. 날카로운데요. 요건 좀. 아이고. 네. Okay, similarly, let's also consider this null space of A transpose. Null space of an A transpose. That is still the same. Okay, so in this case, let's consider back. Let's reconsider this full form. Okay, this is a full form, and this is the reduced form. Okay, and then in the case of a full form, we will obtain the square matrix, right? That has also normal columns, right? And then suppose in this case we have a 30 non-zero values and 20 zero values as our singular values, right? And then what's the size of it? In the case of big example, it will be 100 by 100, right? 100 by 100. So in 100 dimensional space, we initially have full 100 orthonormal basis vectors, right? Then if we have a 30 non-zero singular values, then the first 30 orthonormal vectors will be the also normal basis for the column space of an A. Okay, and then the remaining 70. Okay, remaining 70. So which means we have a 20 non-zero ones. I mean, so 20 zero singular values, right? And then still we deal with the 100-dimensional space, right? And then the matrix rank, or the matrix has 30 non-zero singular values, and then the remaining 70 will be your also normal basis vector of this null space of A transpose. Okay. So in this case, where we have full rank means non-zero singular values is the same as the minimum number between m and n. Okay. Our matrix is full rank, for example. So in this case, 100 by 50, and then yeah, we will have a 50 non-zero singular values, right? And then in this full form, okay, in this full form, this part, the remaining 50 basis vectors will be, the basis, also normal basis for the null space of A transpose. Okay. 이거 다 이해했죠? 아니 뭐 네, 혹시나 뭐 한글로 다시 한번 뭐 요약해 설명하면 하여튼 이게 풀 폼에서 그러니까 하여튼 이게 이게 올소고널 저기 제가 무슨 컴플리멘트라고 그러죠? 무슨 컴플리멘트? 네. 올소고널 컴플리멘트. 이게 이제 우리가 오늘 또 뒤에서 배우게 되는 그 프로젝션이랑 좀 관련이 좀 밀접하게 되는데, 어쨌건 우리 스페이스를 매트릭스 A가 있을 때 이제 so yeah, this notion of also orthogonal complement, I believe I have some slides over here. Okay, so this is a fundamental subspace associated with the matrix A. Okay, so still, I mean, let's just forget about this singular value decomposition. Okay, so we don't just consider it, and then we just look at or deal with this 5 by 3 matrix as an input. Okay, so in this case, we can think of the subspace associated with this this single matrix, which is column space of an A and null space of an A, and column space of A transpose and null space of A transpose. Okay, and then in terms of it, the total dimensions. Okay, the total dimensions. This guy is 5, and this guy is 5, and this guy is 3, and this guy is 3. Right. So these two are connected, and these two are connected. Okay, and then this so just bringing these two, which are both in the 5-dimensional space. So in this case, the column space of an A, if their basis, I mean, if the dimension of this column space of an A is maybe 4, okay, which means it cannot be 4. Okay, let's call it 2. For example, in this case, we have 3 5-dimensional vectors, column vectors in our matrix A, right? And then the column space dimension is 2. What does that mean? We have only 2 linearly independent vectors in three of our columns, right? Okay, so suppose that 2 linearly independent vectors are like this, okay? And then we can always think of the complementary subspace, okay, complementary subspace, which means, okay, given these 2 vectors, now we still yet to fill up the entire space, right, of 5-dimensional space, right? So how many additional vectors do we need to fill out the entire 5-dimensional space? Still, we need 3 more vectors, right? That 3 more vectors, okay? That 3 more vectors are coming from this null space of A transpose. So A transpose, I mean the basis vector of this A transpose is exactly the vectors that you need to fill out the entire 5-dimensional space in, combined with the column, I mean the basis of this column space of an A. Okay, so that's the relationship. I mean that's this complementary relationship between this column space of an A and the null space of A transpose. So that way, it is called orthogonal complement. Orthogonal complement. So those 2 subspaces are orthogonal complement because, I mean, the meaning of this orthogonal complement is that the basis of this first subspace and the basis for the second subspace, if we combine them together and then use it as a single combined space, and then that will fill out our entire universe or entire 5-dimensional space. And at the same time, any vectors from one space and any other vector from the other space, they will always be orthogonal. Okay? So it means they don't have any overlap between them. Okay? So that is the meaning of this complementary relationship. So just to give you a little bit more intuition, like complementary set or the complement in the notion of this set. What is this, right? AC. A and AC, A cup and AC should be empty set, and it is what? It should fill out the entire universe, right? No redundancies, but combining them, and then it will fill out the entire space, right? So that way, we call them as orthogonal complement between these 2, okay? And also this column space of an A transpose and the null space of an A, which are living in 3-dimensional space, okay? So they live in the same space of this 3-dimensional space. They also have this orthogonal complement relationship. Okay? So that way, given any particular matrix A, okay, if we consider these are 4 different subspace formed by our matrix A, okay, then that will give you this kind of meaningful basis set for both 5-dimensional space and also 3-dimensional space, or in general m-dimensional or n-dimensional spaces. Any questions so far? Okay. And then now let's think of the orthonormal versions of this orthogonal complement. Okay. So between this set and this set, you guys now understand what the orthogonal complement is. Okay, to form the 5-dimensional subspace. Okay. So in this case, any vector from here and any vector from there, they are orthogonal. Okay. So that way we call it not just a complement, but we call it orthogonal complement. Orthogonal complement. So any vector from here and any vector from there, they will always be like orthogonal to each other. But what about the basis within each of these 2 spaces? For example, the column space of an A, when considering their basis, then it can be, it may not be orthogonal, right? Okay, so in that case, it is not very clean basis vector, and thus, once we compute or obtain the SVD, okay, SVD then will give you really clean basis set for each of these 4 different subspaces. Okay, and then how? Those are just simply obtained from they are just simply obtained from this, when considering this a full form, okay, full form. And then suppose we identify or we obtain maybe 10 non-zero singular values, okay. Then the first 10, okay, in the left matrix will give you also normal basis vector of the column space of an A, okay. And then the rest of the also normal vectors, okay, in this square matrix or this square orthogonal matrix, the rest of the vectors will give you the basis or the orthogonal also normal basis for the null space of an A transpose. Okay? So again, the column space of an A and the null space of A transpose, they are living in the same space of M dimension space where your matrix is M by M, right? And then similarly, looking at this another orthogonal matrix, okay, if we have a 10 non-zero eigen singular vectors, singular values, and then the first 10 will give you also normal basis for the column space of A transpose, and then the rest of the vectors will give you the also normal basis for the null space of A, okay, which are living in the same living in the n dimensional space of M by N matrix. Any questions so far? Okay, and then let's go back to our main lecture slide. And then here, the lecture 3 is about SVD. And this is another figure of this full form. And this unitary matrix is just the same as orthogonal matrix in the complex number world. Okay, so in the case of complex numbers, then this orthogonal matrix is now called the unitary matrix. And then this is a reduced form, right? And this is some relationship between eigen decomposition and the singular value decomposition, but I will skip that for now. Okay, so once you obtain the SVD, I mean, it's just a simple run of importing the linear algebra library and then calling the function of SVD. Okay, and then that's it. And then you will obtain the U and sigma and V transpose, V matrices. Okay, and then what can we obtain? I mean, as a kind of meaningful information about the matrix, as I discussed already. We can obtain the nice also normal basis vectors for the column space of an A and the null space of an A and their transpose version as well. And at the same time, it just gives you the rank as well. For example, if you have, given maybe 100 by 50 matrix, and then suppose you obtain the 30 non-zero singular values, and then it means your matrix rank is a 30, which means what is the meaning of the rank? The rank is the number of non-zero columns in your matrix. Linearly independent columns, right? And also that rank can be also the same as the number of non-zero rows in your matrix. Okay? So again, the matrix A. If it has non-zero singular values as a 30, for example, and then you have 30 linearly independent columns and also 30 linearly independent rows as well, okay, when considering their row space. And yeah, in terms of their 2 norm and Frobenius norm, it has this interesting relationship. Okay, and then let's also think of the matrix transformation perspective. So yeah, I'm just gonna discuss about this thing that we have studied a lot, right? So in the case of singular value decomposition, okay, yeah, the exact same scenarios will happen, and then I think that was part of our exam, right? So the singular value decomposition will exactly follow this scenario where if we consider this AX, in this case, our matrix A is 5 by 3 matrix, and then this is the 3-dimensional vector, right? And then if we compute the first linear transformation or the matrix product with the V transpose, okay? So V is like V1 transpose, V2 transpose, V3 transpose, right? So in this case, just simply multiplying this V transpose X. In this case, when comparing it with the V, D, V inverse, and X, and then you guys know this part is just obtaining the linear combination coefficient when using the basis as the columns of V, right? But in general, V is not orthonormal or orthogonal vectors, right? Orthogonal vectors. So yeah, it is quite kind of complicated to having to just solve this linear system. But yeah, so this comes from this, right? So V and Y equals X, right? And then this Y is the solution as this V inverse X, right? But what if our matrix V is orthogonal matrix, okay, orthogonal matrix, and then this V inverse is this V transpose, right? So still V transpose X in the case of this orthogonal matrix V, okay, and then it can still be viewed or understood as obtaining the linear combination coefficient corresponding to the basis given in this matrix V. Okay. And then we do the diagonal scaling. Okay. And then in the case of an eigen decomposition, okay, eigen decomposition, we consider this a 3 by 3 matrix or the square matrix, for example, in the case of an eigen decomposition. So in that case, we just change the basis with respect to the columns of V, and then do the diagonal scaling, and then come back, right, by using the same matrix. But in this case, I mean, if entire matrix was 3 by 3, and then the 3-dimensional vector will be transformed into 3-dimensional vector, right? So we can view it as like moving, I mean, we still handle or still deal with the same 3-dimensional space, but using just the different basis vectors, right? But in this case, we just, this is a 5 by 3 matrix. In this case, we just send the 3-dimensional vectors into entirely different 5-dimensional space, right? So that way, we obtain this coefficient and then diagonal scaling, and then when sending it back to some output space, it's no longer be 3-dimensional space, but it's the new or different 5-dimensional space, and so we now have their own corresponding basis vectors, right? But still, we can think of this correspondences between a set of the basis vectors corresponding to input space and their like pairwise corresponding like output vectors. Okay. So that is Yeah, so that is like another perspective of this SVD. Okay, let's see. Let me see. Where I can. Okay, so okay, so here it is. So did I explain this? Okay. A is a 5 by 3, right? And then V is some vector, right? As an input when multiplied on the right. And then this vector is always mapped into some fixed directional vector in the output space, where the output space is 5-dimensional space, but this vector, so this vector is always mapped into a fixed vector. I mean, fixed vector. By that I mean this fixed vector has fixed direction. Okay, so this particular or this fixed directional vector is mapped into this fixed directional vector, but they involve or they just combined with some scaling factor. Okay, so that is our singular vector, singular value, the meaning of the singular value. Okay. So in the case of an eigendecomposition, this V1 should be the same, right? So now we are sending the vector from 3-dimensional to 5-dimensional space, and so the vectors cannot be the same at all, right? But still, we can think of their pairwise correspondences between them. Okay? So V1 is always sent into U1, and then maybe there is another pair. Okay, so that pair comes from like that V1 is sent into the U1, but this combined with this scaling factor of this sigma 1 or corresponding singular value. And then the second one, V2, can be viewed as another eigenvector, okay, kind of eigenvector. And that vector is also has its own fixed directional vector in the output space. Okay? So that way we can think of these pairwise correspondences. But they have these, they involve this scaling, additional scaling factors. Okay. And why do I explain this? Why do I discuss this? Yeah, for example, we can think of this kind of thing. Okay. So did I explain or discuss about the intuitive meaning of this determinant? So the determinant is like we consider the unit square, the unit unit hypersphere, or maybe unit cube. I mean high dimensional cube. Okay, and then when mapping this unit cube or unit sphere into, when multiplying the matrix A for every vector in our unit cube or unit sphere, and then what will be the corresponding volume? Okay, so you guys remember this figure, right? So when handling this 2x2 matrix, and then we can initially think of this unit circle that can, suppose this has the volume or the area as some value, okay? And then we will have the two eigenvectors among many different directional vectors, and then those two eigenvectors will have, when mapping through the matrix A by multiplying matrix A, and then the first eigenvector will have maintained the same vector direction, but that will be scalar. Scaled by the eigenvalue, right? And that way, if this direction has changed with the amount or the scaling factor as 5 and maybe 3, for example, in the case of an values are being 5 and 3. Okay, and then for these two elements or two different vectors having different directions, then each one direction has been stretched out by the factor 5 and 3, and then the area, area is multiplied, or the area is expanded by the ratio of the product of these two eigenvalues. And 5 by 3, which is 5 times 3, which is 15. Right? Okay. And so we can understand this determinant of a matrix in this manner. Okay? So the determinant can be represented as this singular value decomposition, and the determinant is defined only for the square matrix, and then the square matrix has some eigenvalues, and their product will be this determinant, and their physical meaning or intuitive meaning is how much the volume in this corresponding space have been expanded, okay, by what ratio. So that is the meaning of this determinant, or the meaning of the product of all the eigenvalues, right? So that was the meaning of this determinant. Okay. And then you can think of, from that same perspective, we can impose that perspective to intuitively understand why this Frobenius norm of matrix A is this value. So I don't give a intuitive explanation, but so what is the Frobenius norm? What is the Frobenius norm? It is simply the element-wise square the sum, and then take the square root of it, right? So that is the meaning of this Frobenius norm, right? And then let's see. Let's imagine our column space of an A. Okay? Column space of an A. And then if we imagine their singular value decomposition, then our matrix U, which is left singular matrix, okay, left singular matrix, will give you the orthonormal basis of this column space of an A, right? Okay, but if we think of this A times X, okay, A times X, then suppose this vector X is like they are decomposed into the linear combination of the basis with respect to the basis given in this V, right? And then for each component we will have a scalar scaling corresponding to each of our singular values, and then we represent it as another orthonormal basis vector given in our matrix U, right? Okay, and then here, it is a little bit tricky to explain, but there is a kind of this notion of like we preserve the lengths of the vectors as long as we convert our coordinate by using the orthonormal basis vector. For example, so what is the L2 norm of this vector? Then we know that this is our L2 norm, right? But now we change it, this guy with respect to another basis set. For example, like this guy, maybe this guy, okay, which are not orthonormal, right? In this case, we will have their corresponding coefficients as the scalar multiple of this given basis vectors, right? And then in that case, we can imagine their norm with respect to this new representation, new coordinate system. Okay? In that case, yeah, the vector norm or the vector length, I mean, it's approximately like 2.5, and then it is approximately 0.8, for example, and then 2.5 squared and 0.8 squared. So this one, yeah, will be of course not equal to the original vector norm, right? But if we use our new basis as maybe another also normal set of basis vectors, which has the length of 1 and angle of 90 degrees. Okay? So in this case, we can draw their parallelogram or the rectangle representing that point, right? Then we can think of their scalar multiple with respect to the new basis. But in this case, yeah, in this case, this, I mean the vector norm, I mean in terms of the 2 norm, so it will still be the same as this value. So does it make sense? Okay. Okay, so you guys are not looking good. So yeah, this L2 norm is basically computed based on the Pythagorean theorem, right? By just forming the triangle having a right angle or 90-degree angle, right? So in this case, we just formed this triangle by using the original basis. But now we formed another triangle, but still having the 90-degree over here, okay? Right? So we can have many different versions or ways of forming the triangle having the 90-degree angle, right? But still, if we consider the sum of the squared sum of these two line segments in our triangle, and then if we sum them up due to our Pythagorean theorem, then it will always give us the same value corresponding to the squared value of this line segment. I mean the length of this line segment, right? And also, we also already studied as like, yeah, consider this U as orthogonal matrix, okay, and then U transpose X is the corresponding coordinate, right? Because U and Y should be equal to X, right? And then, yeah, we know that U transpose U is identity. So this simply gives us the corresponding coordinate with respect to the new basis, right? And then, yeah, we know that U is orthogonal matrix, and then U transpose is also orthogonal matrix, right? Because U transpose U is identity in the case of square matrix, and then it is U transpose is also identity matrix, right? So we discussed about this before, right? And then, so in this case, what is the norm of these? Yeah, so X transpose U transpose X, and then this should be identity, and so yeah, we don't change the two norm of the original input vector x, right? So I just explained it in this geometric kind of sense, right? Okay. Okay, and then yeah, let's think of this V transpose, okay? V transpose, which is the orthogonal matrix, okay? Orthogonal matrix, and then it's like the transformation that I just described over here, okay? Which maintains their squared sum as the same as the input matrix, okay? But still, in this case, we actually apply the diagonal scaling by using this sigma, right? And in this case, what will be the resulting vector norm? Okay? What will be the resulting vector? So it's like 3, 4, okay? 3, 4 was decomposed with, was represented as the new coordinate system as maybe 2, okay, so this line segment is square root 21, and this line segment is just 2, okay? So suppose that is our new coordinate system. The new coordinate with respect to the new basis, okay? Also normal basis, okay? So in this case, once we obtain that, then we apply the diagonal scaling, right? Diagonal scaling. So we just multiply this guy with the first singular value and the second singular value, okay? And then what will be the vector norm? Okay. So the vector norm will be this guy squared and this guy squared and something like this, right? Okay, so this is the new vector norm after doing the diagonal scaling with respect to the singular values, right? Okay, so it means that in this geometric sense, so we still maintain the triangle that has the 90 degree. And in the case of a higher dimensional space, we will still consider this, right, the volumetric shape of this triangle that still have a 90 degree for each axis, right? Because we still have this orthonormal basis. And then for each of these directions, we just do the diagonal scale by using the singular values, right? And then when combining the vector norm, we can think of the new vector norm computed as this, right? And then, and then let's just simplify this scenario of like the not exactly a unit vector, but consider we have just a 1 by 1, okay, which is just the sum of the two standard unit vector, okay, standard basis vector, and then they will be transformed into another kind of 1 and 1 as a new coordinate system. And then I should explain in this form. So having a vector that has starting with the vector that has the unit norm, okay, something like this, and then this guy, whether it is considering this old coordinate system and also like this new coordinate system, they will still have the L2 norm as 1, right? But for each of these vector lengths, okay, we just individually scale those vector lengths by using our singular values, okay? And then their vector norm will be just computed in this form, singular vector, the squared value of these singular values. Okay, then yeah, it may not be logically. I mean, it is not fully comprehensive. I mean, yeah, my explanation is a little bit imperfect, but let's just forget about the detailed proof or explanation about it. But yeah, let's just get some brief and intuitive idea about the meaning of it. Okay, so once we obtain each of these new vector coefficients, I mean the coefficient with respect to the new basis of V, okay, and then we do the diagonal scaling, and then when considering their L2 norm, and then those singular values will be squared and then added together to form the new vector norm. Okay. Okay, so yeah, you guys should be able to find the rigorous proof about what this means, but yeah, let's just think of it as like considering the new coordinate, and then the scaling factor will just make your L2 norm as this form of the sum of this is squared singular values. Okay, any questions so far? Okay, then yeah, let's take a break for 10 minutes. Then start with at 11:55. Okay, let's continue. Okay, and then yeah, let's briefly discuss about other useful characteristics of the singular value decompositions. So yeah, one widely used application of this singular value decomposition is this low rank approximation. Okay? Low rank approximation. So what is the low rank approximation? Yeah, even before relating this problem with low rank singular value decomposition, let's just discuss the problem setting of this low rank approximation. Okay, so suppose we are given the matrix A, then you want to represent this matrix as another matrix that has much lower rank compared to the original matrix A. So if the original matrix A is maybe 100 by maybe 80 matrix, and then usually the rank of this matrix will be like 80, assuming that it has a full rank. And then given this matrix, we want to represent this matrix as having this rank of this low ranked version of the same matrix A as maybe 30, for example. Okay, so this is our target rank of our low rank matrix, and then we want to approximate this original matrix with this low rank matrix. Okay, so in this case, how can we represent this similar matrix or approximate relationship between them? We basically subtract or compute the difference between these two matrices. So if in terms of base size, if the matrix A has 100 by 80, and then AR will also have 100 by 80. Okay, so we assume it has the same matrix. Okay, in this case, we just subtract between these two same sized matrices, and then consider their Frobenius norm. Okay, so this one can be minimized. Okay, so that way we can think of this AR as a low rank approximation, because at each element is as close as possible to the original element given in the original matrix A. Okay, so it's like this. Suppose we are given this matrix that has the rank of 2. Okay, and then we want to obtain the low rank matrix that has the rank of 1. So in this case, 1, 2, 4, and 2, 4, and 10. So in this case, let's just compare each element in these two matrices, 1 and 1, and so on, and then only these two values may have a difference, right? Okay, so in this case, except for this entry, so all the others are the same, right? So it can be viewed as one kind of approximate version of the original matrix, but still the rank is 1, right? Okay, so in this case, let's just change this value as maybe 5, and then now the difference is also occurring between these two elements as 1, right? In terms of an absolute value, and between these two, we have an absolute value difference between these two as 2. So in this case, the Frobenius norm between these two matrices will be like 1 squared and 2 squared, right? So this is our Frobenius norm difference. Okay, so given this original matrix, this matrix having the rank of 1, I mean, what is the optimal solution? Optimal matrix, okay? That minimizes the difference between this input and the low rank matrix in terms of a Frobenius norm sense. Okay, so that is the matrix approximation or low rank approximation problem. And interestingly, so in this low rank approximation problem, so we usually set our target rank as maybe 1, and in this example, we set it as a 30, for example. Okay, so given this problem setting, the optimal solution for this AR is naturally obtained from the singular value decomposition. So in other words, once we obtain the singular value decomposition of this A, okay, and then this optimal solution that minimizes this problem. Okay, the optimal solution of an AR is just a truncated version of our SVD. So for example, let's use this figure. So let's start with this reduced form of an SVD. And then suppose our low rank is given as maybe as 2, for example. So let's get back to this simple 3x3 case where our singular values are 5, 8, 5, and 2. Okay. So in this case, what is the rank 2 row rank approximation? In this case, that matrix is simply obtained by just set the third one as 0. Okay. And then maintaining the largest singular values, that has the same value as the number of, the target length that we are given. Okay. So in this case, we set our target rank as 2. So in that case, we simply just choose 2 largest singular values. Okay, and then their sum of rank 1 outer product form, and then we will just have only 2 of the first rank 1 outer products. Okay. And then why is it having a rank of 2? Okay, why is it having the rank of 2? Okay, so we have these 2 orthonormal columns, right? Orthonormal columns. And then let's just merge this scalar into this row vectors of V1 transpose and V2 transpose. And then we just rearrange these as this one and this one. And then, this guy and this guy. So going back to this form where this part is merged into the right matrix. Okay. So that way, our matrix on the left will have only 2 orthonormal columns, and thus we can verify that the rank is 2. Okay. So, so this is our low rank approximation solution. Best low rank approximation solution in terms of a Frobenius norm sense. Okay. So I didn't give you any proof about it, but you can have this kind of intuitive characteristic or relationship between this low rank approximation and the singular value decomposition. Okay, and then although it is not widely used or less used compared to this Frobenius norm sense, but we can also rank low rank approximation in terms of a 2 norm sense. For example, given the rank as this number, and then that matrix can be represented as this, and then when just minimizing the 2 norms, 2 norms of the difference of our matrix A, which is the full rank matrix, and the low rank matrix. Okay. So in this case, when using this 2 norm, the solution will still be the same. The solution will be just a truncated version of this SVD by just maintaining the k largest singular values and their corresponding components. Okay, and then let's think of their minimum possible or best error, for example, in the case of 2 norm sense. So what will be, when achieving the best solution for this low rank matrix, and then what will be there are two norm differences between the original matrix and the best rank K matrix. So in this case, yeah, interestingly, the two norm, I mean the best possible two norm difference, or the minimum two norm difference between this original matrix and this guy is sigma. What is it called? 뭐라고? 네? 누? 이건가요 혹시? 누? Okay, so let's just call it as K, using the simple alphabet. K. And then, intuitively, once we obtain this truncated version of the SVD, and then given this sum of the rank 1 outer product sense, so we pick up just the two largest components, and then we just subtract this part from the original A part. Okay, and then we will just remove them, and then the remaining part will form our new matrix as a difference between these two matrices, right? So in that case, we know that some matrix 2 norm, so given a matrix, and then its 2 norm is the largest singular value, right? So the 2 norm definition is defined as this. Right? So we freely change the direction of our vector A, vector X, and then we pick up such a vector that maximizes their vector length, okay, in the resulting vector after this matrix multiplication. Okay. So in that sense, we know that given an arbitrary vector, and that arbitrary vector can be decomposed with respect to the new basis, which are the singular vectors of A, right? And then when aligning the given vector X and their direction with the singular vector that has the largest stretching ratio, scalar multiple, okay? So that way we can maximize the vector length of this resulting vector. Okay, so after multiplying this largest component, I mean K largest component, and then in terms of the remaining component, and their largest component will be this guy. Right? So that way, the lowest possible error will be this singular value at the K plus 1's position. Okay. And then also, it's in terms of its Frobenius norm sense, this so this is related to what we discussed in the previous I mean before our break. So I'm gonna skip this part as well. 네.
베스트 랭크 어프로치메이션 부분에서
네.
저게 이제 K 플러스 1번째만 남는다는 게 예를 들어 랭크가 R이면은
네.
R-1번째까지를 다 사용해서 A, K를 만든다 이런 식으로 이해하면 됩니다. 그러니까 싱글 밸류가 하나밖에 안 남아서 아래 곱식에 이제 예를 들면 뭐 R제곱밖에 없는 거예요. 그러면 루트 R제곱이니까 루트 시그마 R제곱이니까 시그마 R만 남아서 저렇게 된다라고 생각을 했었는데
네.
그러면은 이제 그러니까 베스트 어프락시메이션이라는 게 결국은 R개의 랭크가 있을 때, 그러니까 R개의 베이시스가 있을 때 그 중에 R-1개만 가지고 어프락시메이션을 한 게 베스트다 이렇게 받아들이면 되는 거예요.
잠깐만요. 우리 타겟 랭크가 R이에요 지금? 타겟 랭크가 R인 거예요 지금?
저쪽에 이제 A가 랭크가 R이라고 되어 있어요.
네. 네. 그러니까 이게 여기가 좀 노테이션이 뭐 좀 네. 요게 이제 네. 이 R은 그러니까 오리지널 매트릭스 랭크이죠. 그다음에 누가 우리의 타겟 로우 랭크이고요. 네. 그리고 이제 매트릭스 그 어프락시메이션을 투놈 센스에서 했을 때 이제 네, 어디까지 이제 우리가 할 수 있느냐? 이제 네. 하여튼 뭐 맥심 그 largest singular value를 그 누의 개수만큼 우리가 취하고 그랬을 때 남는 어떤 에러 그러니까 그런 베스트 솔루션을 취했을 때 A와의 여전히 그 차이, 그러니까 결과적으로 남는 차이가 얼마냐? 투놈 센스에서는 이렇다는 거고요. 네, 그 다음엔 이제 프로비니어스 놈 센스에서는 오타가 있네요. 이게 투놈이 아니라 이게 프로비니어스 놈. 예. 약간 아까 내가 좀 설명을 좀 하고 싶었던 거는 이제 뭐냐면 이제 매트릭스가 그 어떻게 보면 그 싱귤러 밸류 디컴포지션 하면 다 이게 수직인 컴포넌트로 분해가 되고 그 매트릭스가 좀 아까 그 부피가 뭐 각 방향별로 이렇게 싱귤러 밸류 혹은 그 아이겐 밸류만큼 이렇게 배수가 되면서 이렇게 어떤 부피를 이렇게 키운다라고 이야기를 했잖아요. 각 디렉션으로. 그게 그러니까 변환을 그러니까 매트릭스를 어떤 뭐 정해진 부피가 있을 때 각 컴포넌트별로 이렇게 스트레치 이렇게 늘리고 줄이고 해서 이제 생기는 그 부피. 네. 하여튼 그렇게도 이해를 해볼 수가 있고 아니면 그 매트릭스 자체로서는 그 매트릭스의 프로비니어스 놈이 가지는 의미가 뭐냐면 그 매트릭스가 가진 어떤 질량, 그러니까 매트릭스가 가진 어떤 총량 같이 생각을 해볼 수가 있어요. 총량. 그렇잖아요. 뭐 엘리먼트들을 다 제곱해서 더하는 게 총 길이 아니면 양이라고 생각할 수가 있고 근데 이제 그 양이 결국 다름이 아니라 우리의 싱귤러 밸류들을 제곱해서 이렇게 다 합친 그 양이 우리 그 매트릭스가 가진 총량이라는 뜻이고요. 네, 총량이라는 뜻이고 베스트 로우 랭크 R 여기서는 랭크 누 아니면 K라고 하죠. 랭크 K로 어프락시메이션을 하면 그러면 이제 우리가 그 베스트 솔루션이 그 싱귤러 밸류 디컴포지션에서 그 라지스트 그거를 뽑은 그게 솔루션이 왜 나와야 되는가 그거는 이제 증명은 하진 않았지만 증명을 한번 찾아봐도 좋을 것 같아요. 증명을 하진 않았지만 일단은 직관적으로 이해를 할 때는 그렇게 이제 랭크 R, 랭크 K 개만큼 우리가 유지를 한다라고 그러면 그 매트릭스가 가지고 있는 총양 중에서 이제 최대한 잘 보존할 수 있는 게 처음 그 K 개만큼 그만큼을 네, 우리가 그 양을 우리가 유지 혹은 프리저브를 할 수가 있다는 뜻이 돼요. 네. 그럼 거꾸로 잃어버리는 양은 뭐냐? 잃어버리는 양이 지금 여기서 나오는 식이 돼요. 잃어버린 양은 이제 그 뒤쪽에 우리가 어쩔 수 없이 이제 싱귤러 밸류들을 다 0으로 만들어 주겠다. 거기서 이렇게 잘라서 뒤쪽에 탈락하게 된 그만큼 우리가 잃어버리게 돼요. Okay, so yeah, in other words, we can think of this the sum of square the sum of singular values as the total mass that our matrix A has, and then when just obtaining the best of rank K approximation matrix, and then we can intuitively think of it maintaining or preserving the maximum possible mass of the original matrix A as the sum of the first K elements of the squared sum of the first K singular values. Okay. So that's the meaning of this low rank matrix approximation. Any other questions? So this low rank approximation is quite closely related to dimension reduction. Okay, so if you studied, for example, PCA or principal component analysis, and then the problem setting is slightly different, where So suppose our input matrix is m by n, and then suppose this is our feature by data item matrix in the context of a machine learning. Okay? Then each data item is represented as an m-dimensional vector, where each of these dimensions represent some feature like height and weight, blood type, or maybe location of a residence, and so on. Okay, and then we want to reduce the dimensionality, I mean the original number of features that we are initially given, and then we want to obtain this new representation that has a smaller dimensions. Okay, so this is the dimension reduction task. Okay, so here, I mean, there are many different objective functions that we can consider in the task of dimension reduction, but one task will be given this matrix A. Okay, and then we want to somehow relate this matrix. So let's call this as an x and y. Okay, we want to somehow consider the difference between them. Okay? But it doesn't even make sense because the matrix A and B has different size, right? A has m rows, and x has an m rows, and y has an r rows. So in this case, we can think of what is the fixed number? Fixed number is the number of data items, and when given the same number of data items, then we can consider their relationships between data items. So if we are given 10 data items, and then we can consider their pairwise inner product as their similarity measure, or their Euclidean distance as also as a distance measure. Okay, that characterizes every pairwise relationship between the data items. Okay? And then let's consider their inner product, for example. And then we know that the inner product matrix, given this matrix X, is X transpose X, right? So in this case, suppose our feature is maybe 30, originally 30 dimension, and then this X transpose is like 10 by 30 and 30 by 10, right? And then we obtain 10 by 10, which represents every pairwise inner product as a similarity score between the data items. Okay? And then we can also compute this same measure from this reduced version, reduced dimensional representation of our matrix. Okay, so how? Y transpose Y, right? But here, in this case, the inner product is computed in the original 30-dimensional space, but in this case of Y transpose Y, the inner product will be computed in the low-dimensional space, right? And then now we want to preserve as much as possible every pairwise relationship given in the original space. So in this case, X transpose X minus Y transpose Y, and we want to minimize this. Okay, so we want to solve this kind of problem, and in that case, it can be a valid objective function for a dimension reduction task, because we reduce the dimensionality of Y. Okay, the dimension is R in the case of Y, right? Okay, so here let's add one more constraint. So that additional constraint in this problem is that we can solve this task for any possible Y's, but let's just impose the constraints so that the Y is the linear transformation of the matrix X. Okay, so again, X is our original 30-dimensional space, and then let's set R as 5, and then 5 by 30, for example, and then this is our W. Okay, so in this case, Y is now a linear combination of original features, right, to represent or to obtain the new 5-dimensional vectors. Right? So if we add this kind of constraint, and then the optimal solution for Y is now related to the singular value decomposition. So what is the, so obtaining the best or optimal Y is the same as obtaining or computing the best or optimal W, and that optimal W is obtained as what? So that is, suppose this X is represented as a U and sigma and V transpose as our singular value decomposition. Okay? And then okay, so we pick up this U, okay, and then you will have also normal vectors in 30-dimensional space, right? Okay. You will have the number of rows as 30, of course, right? And then each column vectors will be also normal vectors, right? And then we just simply pick up the the first 5 also normal vectors, right, from U. Okay, and then we transpose it. So given U, so we pick up this 30 by 5, and then we transpose it, okay, 5 by 30. So this will be our solution, or the best solution for this W that transforms this 30-dimensional vector into 5-dimensional vector. Okay, I mean, although I didn't prove it yet, I mean, we will skip the proof, but intuitively, in terms of an inner product sense, maximally preserving the pairwise relationships given our data instances. Then the linear transformation, the optimal linear transformation that maximally preserves their relationship is obtained from the left singular vectors. And also, as I mentioned, we have another relationship that can another way to compute their relationship between the pair of data items, which is a Euclidean distance, right? So let's consider the matrix dx, for example, as all the pairwise Euclidean distance matrix. So dx is still 10 by 10 matrix, but for example, like 5 by 3 component, and that value is indicating the Euclidean distance between fifth and the third data item. Okay, so we just compute this Euclidean distance between every pair in this 30-dimensional space, right? And then that way we can form our pairwise Euclidean distance matrix, right? And then now we consider the reduced dimensional representation of our same data item, and then compute their pairwise Euclidean distance matrix, right? Okay. And then we can formulate our problem as this guy, dx and dy, and then also we can minimize this reduced dimensional representation to minimize their Euclidean distance, the difference in terms of the Euclidean distance. Okay, so in this case, let's also impose this y as the linear transformation of the x. So in this case, the optimal solution, I'm just telling you the conclusion. Okay, so in this case, the optimal solution for w is still the k largest singular values and their transpose version. So that's how this SVD is related to this low rank, dimension reduction task in machine learning. And this is just a, also called a PCA, for example. Yeah, so let's see. Yeah, so this slide is just a formal description of what I just described. Oh, yeah, I forgot to mention one thing. Okay, so one thing is, the additional constraint that we impose here is this W matrix, or the rows of W, is orthogonal. So we need that kind of constraint. Otherwise, this problem could be, this problem, will be a little bit trivial, because, we can just duplicate the same vectors over and over when forming this W. So when imposing the orthonormal rows in the matrix W, or when forming this G transpose, where the columns of G is orthonormal, and then it is the same problem as what we discussed before. Then, as I mentioned, it is related to principal component analysis, and then the singular values. For example, in the case of 5 by 3 matrix, then the singular values are. Let's see. Let's get back to this example of singular value of 8, 5, and 2. Okay. So in this case, considering the feature vector representation of this matrix A. Okay, so suppose each column is a feature vector of our data item. Okay, and then it will be represented as 5-dimensional space, right? 5-dimensional space. And then okay, so when just imagining them, in this 2-dimensional space, and then each data instance will be over here, and so on. Okay. So it is, of course, having more than 3 data items. Where 1, 2, 3, 4, 5, 6. We have 6 data items in the 2-dimensional space, right? And then the feature vector representation of our matrix will have this form, right? And then it will also have the singular value decomposition, right, as 2 by 2, and in full form 2 by 6, and then like 6 by 6, right? And then we will have these 2 non-zero singular values, assuming that this matrix is a full rank. Okay, and then I mentioned that those 2 singular values, the squared sum of these 2 singular values are kind of a total mass that this matrix has, right? And that is the same as, even though I failed to properly prove it, but we know that these squared sum of singular values are the same as the Frobenius norm of the matrix, right? And then the Frobenius norm can be also thorough from the perspective of this feature vector representation in the following manner. So this one is the first data item's first feature and the second feature of the first data item, right? And then the second data item and the first feature, and so on, right? And then what is the Frobenius norm of this matrix? The Frobenius norm is simply just the square sum of all these values, right? Okay, and then you can view it as like, let's consider the sum of the first dimensional values. And then, yeah, so yeah, we need a kind of centering kind of step when considering the PCA. So yeah, let's imagine we initially pre-processed our data items so that their mean is 0 for each dimension. Okay, so in this case, okay, so this is the new feature vector representation after centering kind of pre-processing. Okay, and then yeah, once they are zero centered, and then their squared sum will be their kind of 6 times variance, right? Okay, so that is related to variance, right? So when computing the variance after zero centering, then we will just compute the squared sum of them and then just simply divide it by the total number of data items, right? So the variance is, so when computing the Frobenius norm, and then we will compute the 6 times the variance along the first direction or first axis, and then the 6 times the variance of the second axis, right? So roughly, the Frobenius norm can be viewed as the sum of the variances across different dimensions that we have. Okay. So previously, when talking about the Frobenius norm, I mentioned that Frobenius norm can be viewed as the total mass of the matrix, but from the perspective of a feature vector representation, Frobenius norm can be viewed as the sum of the variances across the entire dimensions. Okay? And then what is the variance when viewing the squared sum for each column? That is this guy, the length of each vector, right? The square sum of these each vector length is also the same as the Frobenius norm, right? Okay. And then now let's think of the new basis, new orthonormal basis. So instead of using the standard basis vector of 1, 0, and 0, 1, then this is new first axis and the second axis. And then, let's imagine we represent each of these data items coordinate by using the new basis. Okay. So in this case, as I mentioned in the earlier example, even after changing this basis, as long as these bases are also normal, and then there are new coordinates, and then their 2 norm, okay, 2 norm will still represent the vector length of each of these vectors, right? So even after changing the basis, the Frobenius norm will remain the same, right? Okay, so why do I discuss this? It is because we want to relate these new bases, or we want to use this new basis as the basis given in the singular value decomposition. Okay? Singular value decomposition. Okay? And then suppose these 2 axes, the first and the second axis, are these 2 left singular vectors, computed from or obtained from this singular value decomposition. Okay. Okay, then this Frobenius norm, yeah, when viewing it as the sum of the variances per each dimension, okay, per dimension, then the total mass or the total sum of these variances will be the Frobenius norm, right? And that Frobenius norm, yeah, is also represented as the squared sum of these singular values, right? So even though we didn't prove it, so we studied this this characteristic, and then that singular value is maybe 8 and 5. Okay, and then even after changing those data items coordinate system, I mean coordinate representations by using these new left singular vectors as our new basis vectors, and then their vector lengths will still remain the same. Okay, and then the meaning of these singular values are now corresponding to the variance of each dimension in this new coordinate system. So what I mean by that is, so let's consider, let's consider the standard basis and their first axis, I mean the variance along the first axis. Okay, and then the first axis will be like this value, because this guy is maybe 5,2, and this will be 5, and then this guy will have maybe 3, -1, and then 3, and then yeah, 5 squared and 3 squared and so on, right? So this one will correspond to the sum of, I mean the variance corresponding to the first axis, right? And then suppose that number is 30, for example. Okay, and then also we can compute the variance along the second dimension. It was 5 by 2, for example, and then 2 squared, and then this was 3, -1, and then -1 squared, and so on. So that's how we compute the variance along the second dimension. And then okay, and 89, 59. So yeah, I kind of cheated so that I can show you the relationship between the two. So suppose the first axis variance is 30 and the second axis variance is 59. Okay, and then the Frobenius norm, I mean the squared Frobenius norm, will be the sum of these two, right? Sum of these two, and we know that this Frobenius norm is 8 squared and 5 squared and their sum, right? And then what is the meaning of this 8 and 5, or a squared and 5 squared? A squared is the variance along the along this new axis. Okay, so in this case, this guy, by using the previous standard basis, the coordinate was 5,2, and then now using the new axis, this is now represented as maybe 9, -1, right? So along the first axis, the new coordinate is 9, the second coordinate is -1. Okay? So that way we can consider their new first dimensional coordinates for all the entire data items, right? And then for example, in this case, it is 2, -40, for example, and then 9 squared and 2 squared and so on. Okay, so this value is 8 squared. And then computing the variance along the new second axis, given the new singular vector, right? And that dimensions variance will be 25. Okay? So that's the relationship between this axis-wise or dimension-wise variance with respect to the new basis determined by our singular vectors. Okay. And in the case of singular values, singular value decomposition, we always maintain the decreasing or monotonically decreasing orders, right? So in the case of an original coordinates, the first dimension may have the variance of 30, and the second dimension will have the variance of 59, and then the third dimension may have the variance as 45. And in this case, along the axis, there is no kind of ordering in terms of this monotonic increase or decrease in terms of their variance, right? But now after rearranging or assigning the new coordinate systems by using this singular vectors, okay, and now their variances are monotonically increasing, right? So this is the relations. I mean, this is how this singular value decomposition is related to principal component analysis. So in this case, the latter dimensions will have smaller variances compared to the previous dimensions, right? And then what if we have to choose some subset of these dimensions out of the entire dimension? So if our dimension was 10, and then each of these 10 dimensions will have now this monotonically decreasing variance patterns. And then let's try to, let's try to reduce the dimensionality into 1 out of the 2-dimensional data. Okay, so let's think of our data. The first data item over here, and the second data item over here, and the third data item is over here. Okay, so what is the meaning of preserving all the pairwise distance? Okay, all the pairwise distance. So the pairwise distance is like this, and this, and this. Yeah, even though it is not a triangle having 90 degrees. Okay, so in this case, the distance is the vector length of these the vector differences between these three. I mean, each of these pairs, each pair of these 3 different vectors, right? So in this case, so let's just choose one of these axes as the reduced dimensional representation. So now let's simplify the task of dimension reduction of choosing one of these 2 dimensions. Okay, so it is like 5, 1, and it is -3, 2, and -4, -3. Okay, and then now let's think of the dimension reduction as choosing the first, choosing either first or the second dimension. And when choosing the first dimension, and then -3, and 5, and -4. This will be our new representation of these 3 data points, right? And then 2 and 2 and 1 and -3 will be the case of choosing the second dimension. Okay, and then which case is better preserving their pairwise distances. Okay, so in this case, we can decompose this vector into this triangle that has the 90-degree angle, right? So when choosing the first dimension of this version, we want to preserve this slanted line segment. But if we chose the first dimension, what is the resulting pairwise distance between the 2 points? That is corresponding to this part, right? So instead of representing the pairwise distance between this one and this one, we now approximate as this line segment, right? And then also in this case, we can draw this triangle, and then instead of using this, we are using this, and then we also draw the triangle like this, and then we are preserving this, right? Okay, so from this we intuitively understand that choosing the first dimension gives a better distance or pairwise distance preservation, right? Because among many of these pairwise difference vectors, okay, the x-axis is more kind of major direction. Okay? So if we have to choose one of them, then we have to choose the maximum one. I mean the one such that it has the maximum variance or the maximum differences. Okay. Okay, so from this perspective of this, from looking at this simple example, we can now combine those singular vectors as the new coordinate system or new basis that we represent these data items. Okay, and then we apply the same ideas. So back to this example, instead of using the original coordinate system that has, like increasing or decreasing variance patterns, we now sort them out in a way that the first axis will have the maximum or largest variance, and the second one as the second largest, and so on, right? And then using the new coordinate system, new coordinate system, and then now it's time to apply this kind of thing, okay? So if we have to choose only some subset of the axis that as a reduced dimensional representation, what kind of dimensions or what kind of directions should we choose? We can simply just choose the first k directions that has the maximum variance along those corresponding dimensions. Okay, and also here we can see one additional kind of characteristic, although it is not not much important, but if we reduce the dimensionality in this manner, and then the pairwise distance will always decrease. Okay, so in this particular case, we want to represent this line the length of this line segment, and then this one is always decomposed with these two line segments through the Pythagorean theorem. This guy squared and that guy squared is the same as the original distance. So if we choose one of them, okay, we can choose the one that has the maximum variance. So that will be our best strategy. But in terms of their pairwise distance, when comparing the original two-dimensional representation and the one-dimensional representation, the one-dimensional representation will always have like smaller distances, smaller pairwise distances. Okay. So pairwise distances cannot be bigger than it cannot be bigger than the original distance for any given pair, any given pair of data items. So that is another characteristic when using this orthogonal kind of projection as our dimension reduction kind of constraint. Okay, so intuitively, let me add one probably last statement about this. So we now sort them out in terms of their variances, right? To represent the data distribution, or how the data are scattered around, right? Scattered away from zero, right? And then if we have to choose the best k axis or best k dimensions, or reduce the dimension into k, and then we will choose the k largest, k axis that has the largest variances according to the singular value decomposition result, right? But at the same time, we are throwing away the remaining kind of axis. So in the case of this example, we threw away this axis that was not chosen, right? So that way, in terms of our Frobenius norm, it can be viewed as the sum of the variances across all the dimensions, right? And then we somehow maintaining the total sum, and then we just obtain another version of orthonormal axis or the basis, but the first one has the largest variance and so on, right? And then we just simply cut and then remove the k plus 1s to the remaining axis, okay, in order to maintain the best k-dimensional representation. Any questions? 네, 뭐 이거 좀 다 이해 가죠? Okay. So that was the that is the content that we need to study about dimension reduction. And also, let's play with those matrix multiplications when we chose the best solution for our linear transformation matrix W. Okay, so overall, what I just described as choosing the maximum variance axis according to our singular value decomposition result is called principal component analysis. Okay. So principal component means like the axis that has the largest variance. Okay, so that way we call it as the main axis or the principal axis, because along that direction the data varies the most. Okay, and then if A was U sigma V transpose, and then when reducing the dimensionality A into, for example, K, and then let's think of this reduced form. And then let's try to reduce the dimension into 2. Okay, and then our matrix W. Okay, so this is an X, and this is a reduced dimension representation of an Y. And then we know that the solution for W, for best low rank approximation, will be like the transpose version of these two column vectors of W as of U, right? Okay, so we pick up the first two column of U, and then so this is the optimal solution for W, and let's call it as W2 transpose. Okay. Okay, and then after multiplying this representation, okay, what will be the two-dimensional representation after obtaining this dimension reduction result? Okay. So in that case, let's just multiply this U2 transpose and original matrix U. Okay. And then first of all, what is the size of the resulting matrix of 2 by 5 and 5 by 3? It is 2 by 3, right? And then, yeah, the resulting matrix, I mean, let me just directly write it down. Along the diagonal, it should be 1. And off diagonal should be 0. And also 0. Okay, so this is because, so initially we have 3 orthonormal columns in our U, and then we pick up the 2, and then form it as a transposed version of our matrix. Then in this case, this guy and this guy, their inner product will be computed as 1 because it's the same, I mean the inner product with the same vector. And then the second one and the second one will form another 1, right? And then what about the cross terms? The first one and the second one, we will produce 0 because they are by definition also normal vectors. And then also this guy is another cross term of the second and the first vector. And then what about this part? Okay, so this is another also normal vector that we didn't choose, right? But still, computing the inner product with this guy, okay, this guy and this guy will produce 0 and also 0, right? Okay, and then now it's time to multiply this diagonal matrix, okay, with this matrix. And then, yeah, what is the resulting matrix? First of all, size is still 2 by 3, right? And then this part is identity, and this part, yeah, is 0, right? Okay, so yeah, it is really simple computation, but let's think of it in this form. So we have two rows, and then now apply the row combination, where the first row is providing the linear combination coefficient of 1, 0, 0 and 0, 1, 0. And then the first one is choosing the first row in the right matrix, right? So yeah, 8, 0, 0, which is picking up the first column, first row. And then what about the second row? And the linear combination coefficient is a 0, 1, 0, and then applying that as a row combination coefficient, and then it is 0, 5, 0, right? Okay, then we further multiply it with this V transpose, right? V transpose, and then yeah, simply it is, yeah, by applying the same strategy or same process of row combination coefficient, and then A00 is applied as a row combination coefficient, and then we are just scaling this as by 8 and this guy by 5, right? Okay, so yeah, our conclusion in this PCA as a dimension reduction process is that, yeah, when picking up the linear transformation matrix over here as the first k columns from this left singular vector v, left singular vector u, okay, and then once we multiply that with the original matrix A, and then what is the resulting dimension reduced representation? That representation is, yeah, we just pick up the same number, I mean the k number of diagonal elements, and also the same number of, I mean k number of right singular vectors. Okay. So that is our reduced dimensional representation. Yep, so in general, using this figure, so we pick up the k column and then transpose it and then multiplying it on the left, and then the result is the same as we pick up the k row and also k row, then combine them. That's it. So that is the result of the PCA. Okay. So any questions so far? Yeah, there are many other stuffs that we can discuss about this singular value decomposition and the principal component analysis, and there are many different characteristics that we can extract out. But yeah, let's just finish this singular value decomposition topic at this moment, and then move to the next topic of this projection and QR decomposition. So even though not much time is left, but yeah, let me just do as much as possible. Okay, so we are now dealing with some projection that we briefly discussed maybe in the last lectures. So by definition, this projector is a linear transformation matrix that satisfies this relationship of this idempotent, right? Idempotent relationship. And of course, the orthogonal projection is satisfying this condition, but the projection, we can think of the non-orthogonal projection. Okay, so in this case, let's look at this figure, and then projection can be understood as like throwing out some light in parallel, right? So let's imagine some sun over here that sheds the light. Okay, the light, the direction of these light are all in parallel. And then the light direction is something like this. Okay, and then given some point, and then this one is our length, okay, or our plane, and then this one is in the middle or in the air, and then we can think of its shadow, okay, due to this light shedding, okay, and then this point, more exactly, the coordinate of this point is the result of this projection in this vector space. Okay, so this one is point, and this one is also the point along the surface, right? So those can be viewed as a vector, right? And this space can be like two or more, higher dimensional space, right? But still, this projection direction is still the same. Okay? And also, that direction can be a line, but that can also be a plane as well. But we can discuss it more in detail. As we go through some more examples. Okay, so still, even in this case of non-orthogonal projection, so here the angle between this surface and this light direction is not 90-degree angle, right? So this one is example of non-orthogonal projection, right? But still, even in this case, this p squared being equal to p is satisfied because this guy is projected onto this point, but this is already on this surface, and then even after applying the projection once again, the point will still remain the same. Okay, then let's just relate the intuition that we can think of in this projection projection transformation with this idempotent relationship. So roughly I mentioned this line as a surface, but this surface is defined as the subspace the subspace created by this matrix multiplication of px, right? So this projection is anyways represented as a linear transformation or the matrix multiplication with the original vector, right? And then all the possible resulting vector after this matrix multiplication will be just the range of P, okay? Or it is the column space of P, right? Because X is a vector and P times X is a linear combination of the columns in P using the coefficient as X. Okay, so if input vector X or V is already in the range of P, okay, so in this case it is the situation where this V is already inside of this surface. So in this case, we know that intuitively this additional projection of P should be the same as the original point P, right? Okay, so how can we prove that? Okay, how can we prove that? So if V is inside of the range of P, then this V can be represented as a linear combination of the columns of P, right? And it means that for some other vector X, there should be a vector X that is representing this vector V as a linear combination of columns of P, which is Px, right? Okay, so in this case, even though we didn't explicitly obtain or computed this X, we know that V is represented as Px, and then P times V will be equal to P squared times X, even though we don't know X exactly, but in this case we just apply this P squared is equal to P, and then okay. And also this is a projection along the line. So in this case, the projection can be viewed as a decomposition of the original vectors into the two different vectors. So okay, so suppose this is our origin, and this is the original vector V, right? And this vector V can be represented as the sum of these two vectors. The first one is this PV, right, which is the resulting vector after this projection. And then we can think of this vector, which is representing the direction of shedding lights. Okay, so this direction of the lights that creates this shadow. Okay, so that direction is corresponding to this guy, right? And then that component can be represented as V minus PV. Okay, so PV is the resulting vector after projection, and subtracting it from the original vector. Okay, so that component of V minus PV is representing the direction of our light. Okay, so that is called projection. Okay, projection line. Okay, and more interestingly, this part. Okay, this part is inside of the known space of P. which means that this P times PV minus V, because the null space definition is PX should be equal to 0. Okay, so this one should be equal to 0. Right? So what does that mean? Okay, so yeah, let me just point out one last intuitive characteristic about that. So let's consider this vector. I mean this vector, okay? And then this vector is part of our null space, which means this vector times our matrix P should be equal to 0, and then it means that this P times some vector is doing the projection, right? And then this direction, and then we project that point or this vector, and then we additionally project this vector, and then the projected point, the resulting point after this projection is always 0. So it's like, so whatever direction that the lights are shedding, okay, and then we have some vector, okay, but that vector, after projecting that vector, and then it will always end up with the 0, the origin vector. So that's the meaning of this null space. I mean, this component is part of our null space. And yeah, the proof is simple. So okay, so so the time's up. So yeah, let's continue next time for this remaining, the rest of the story about this projection. Okay, thank you very much.
교수님이 말씀하신 게 여기서 이제 SVD 컴포지션 컨버전 할 때 랭크를 줄일 때 요거를 곱하면 된다고 하시는 건가요? 근데
네.
그러면 여기서 이 연산을 하는 방식이 그러면 보통은 컴포지션에서 디멘전을 줄일 때 보통 이제 여기서 큰 값을 가져와서 보통 뽑잖아요.
네.
그러면 그거에서 이 두 개를 뽑는다는 건 그냥 단순하게 그냥 유에서 그거에 상응한 두 개의 그 컬럼을 로우를 가져오면 된다.
네. 그건 왜냐하면 여기 싱귤러 밸류는 항상 이게
네.
그 non increasing 오더로 이렇게 쪼로록 되어 있기 때문에 그렇거든요. 그 과정
무조건 크게 그러면 위에서부터
네.
차근차근
네, 맞아요.
크기가
네.
정렬이 되는 거죠.
네. 그걸 우리는 항상 가정을 해요.
그거를 가정을 하는
네.
거예요.
싱귤러 밸류 컴포지션은 그러니까 그렇게 나타내는 게 전혀 어렵지가 않거든요. 그러니까 여기서도 쏘자. 네, 이게 이제 이렇게 나타낸 거를 이렇게 다 분해를 할 수가 있잖아요.
네.
근데 이 더하기는 막 우리가 뭐 마음대로 이제 바꿀 수 있잖아요. 순서를. 네, 그러니까 여기가 뭐 8, 5, 2가 뭐 5, 8, 2 대 요 이제 첫 번째, 두 번째 여기서 첫 번째,
네,
두 번째
네.
뭐 이렇게 바꿔주면은 결국은 결과는 똑같거든요. 그러니까 이제 그게 뭐 굉장히 트리비얼하게 이렇게 변경이 될 수 있기 때문에
네.
우리는 항상 이거를 이제 큰 순서대로 이렇게 나열을 한다고 가정을 해요.
사실 그거를 그러니까 보통 컴퓨터에서 연산을 하게 만들려고 할 때 그렇게 정렬하는 방식을 이렇게 분해해서 보통 한다는 거예요.
그렇게 일단 나타내는 게 일단은 전혀 어렵지가 않은 거잖아요.
네.
그러니까 설사 이게 정렬이 안 돼 있는 채로 얻었어도
네.
그 그냥 정렬하고 이쪽에서도 컬럼 리오더링, 여기 로우 리오더링 하면 되는 거니까.
네.
그러니까 일단 근데 뭐 이런 거 저런 거 이제 뭐 그러니까 전개를 해 나갈 때
네.
뭐 이게 소팅이 안 돼 있으면 하여튼 우리가 소팅을 해갖고 이렇게 처음 거를 잘라서 쓰는 경우들이 많으니까
네.
일단은 소팅을 그렇게 해둔 버전을 SVD의 정의 자체로 생각을 한다는 거죠. 그래서 여기서도 이제 SVD가 이제
네.
이렇게 뭔가
네네네.
요 정의를 달고 가는 거예요. 근데 저 정의는 뭐 전혀 이렇게 뭐 제가 어떤 역할을 하는 건 아니고 저렇게 소팅 안 돼 있어도 그냥 얻을 수가 있는 거죠.
네, 알겠습니다.
네.
감사합니다.
네.
이거 프로젝션 하실 때요.
네.
이거
네.
이게 PV 마이너스 V 벡터가 이 벡터를 말하는 거잖아요. 그럼 이걸 다시 또 P를 곱하는 건 이걸 또 프로젝션 한다는
그렇죠.
건데
네.
어,
네.
기하학적으로 좀 이게
그래요. 네. 이게 여기서 이제 V 빼기 PV는 네. 그러니까 지금 요 벡터잖아요.
예,
요 벡터.
예.
근데 요 벡터를 우리가 프로젝션 할 때는 일단 요 벡터를 어디로 갖고 오느냐? 일단 이 원점으로 갖고 오는 거예요. 요거를 좀 이야기를 명시적으로 했어야 되는데 이제 요게 차이 두 개에 의해서 이루어지는 차이 벡터이긴 하지만 요 벡터 하나를 따로 생각할 때는 우리가 요게 이제 항상 우리는 요 벡터가 이제 원점에서부터 시작한다는 거잖아요.
예.
그러니까 이 경우에는 여기서 프로젝션을 이제 하면 이 벡터는 이게 뭐야? 이 빛의 방향이 항상 똑같이 이렇게 되어 있으니까
예.
항상 프로젝션은 이 원점으로 오게 돼요.
알겠습니다.
교수님 저기 2차원 공간에서 그 랭크 1인 스페이스에 대한 널 스페이스는 항상 그 수직인 직선 아닌가요?
네.
그러면은 저기 V-PV가
네.
P의 널 스페이스면은 결국에 저것도 이거랑 수직이어야 되는 거 아니에요?
네. 이게 그러니까 수직이 여기서 이제 수직이 안 될 수도 있다라고 이제 이야기를 하는 건데.
네.
네.
근데 이전에 배운 거랑 서로 모순돼가지고 어떻게 되는 건가요?
아, 네. 그러니까 이제 우리가 올소거널 매트릭스를 다룰 때는
네.
그리고 저기 리스트 스퀘어나 이런 거를 할 때도 우리 매트릭스가 애초에 올소거널 컬럼이 그려지지 않고 그냥 리니어리 인디펜던트 컬럼이 뭐 이렇게 돼 있으면
네.
거기로 뭐 이렇게 프로젝션을 시킬 때 그때 우리가 항상 썼던 거는 올소거널 프로젝션이었어요. 그러니까 올소거널 프로젝션을 해야만 이 주어진 어떤 포인트가 이 A의 그 컬럼 스페이스의 가장 그 베스트 어프락시메이션으로서 우리가 동작할 수가 있으니까. 그러니까 거기서도 이제 우리는 올소거널 그 프로젝션 썼었고요. 근데 그러니까 실질적으로는 올소거널 프로젝션이 아마 거의 10중 8구 올소거널 프로젝션만 쓰여요. 뭔가 프로젝션 할 때는. 근데 이제 프로젝션의 정의 자체는 여기서 이야기한 것처럼 이제 딱 이 조건만 만족을 하면 되는 매트릭스인 거예요.
근데 이 조건도 반드시 만족할 수밖에 없지 않아요?
네.
그걸
그러니까
만족을 하면.
네, 그렇죠. 저걸 만족하면 이것도 만족하는 거죠.
근데 요거는 요거잖아요.
네? 그렇지가 않은 거죠.
않아요?
네. 그러니까 아까의 그 예제는 그 특별한 그 올소거널 프로젝션 일대의 예제를 가지고 이제 생각을 하고 있는 건데 그 경우는 올소거널 프로젝션이니까 이게 맞는 건데 여기서는 그러니까 어떤 뭐 P가 올소거널한 혹은 올소노멀한 컬럼을 가져야 된다라거나 뭐 이런 가정이 지금 전혀 없었잖아요. 지금 요 한 장 내 슬라이드에서의 스토리는
근데 벡터의 기본 그거 자체가 해서 0이 나오고 그러려면은
네.
수직이어야 되잖아요.
네. 근데 여기서는 그러니까 얘랑 곱해서 이제 0이 나오는 거예요. 근데 이게 여기서의 이 벡터가 여기서의 P에서의 이 로우 벡터랑 수직이 되어야지. 널 스페이스라는 게 기본적으로 이제 AX 이꼴 0이라고 하는 거는 A가 뭐가 이렇게 있다라고 할 때 X가 이렇게 있다 그러면 이제 여기서 이 첫 번째 줄과 요게 이제 0이어야 되고 요것과 또 요게 또 0이어야 되고 이런 거잖아요. 네. 그러니까 그 조건은 맞아요. 그 조건은 맞는데 여기에서 그러니까 마찬가지로 요 PV 빼기 V라는 벡터가 요 P에서의 각각의 로우랑 올소건을 한 거는 맞아요. 네. 그런데 네. 여기서 뭐 어떤 그 프로젝션 방향 자체가 지금 이거가 이제 뭔가 이
제가
레인지
여기를 P7로 생각했네요.
네네네.
고맙습니다.
네.